Hello and welcome to Empowered Learning. This is the third video in the Calculating Volume of Solids series. And now what we're going to do is calculate volumes of solids where the actual solid is formed by taking an area that is defined and rotating it about either a vertical or horizontal axis. So for this first example, we are told that we want to find the volume of a solid obtained by rotating the region bounded by the given curves about this specified line. So here we have the area bounded by the square root of x, y equals 1, and x equals 0, and we want to rotate it about the line x equals 1. So if we produce that graph here, we'll start off with square root of x, which is here, y equals 1, which is this particular line here, and x equals 0, which of course is just the y-axis. So we want the area basically that's bounded by all this in here. Okay. So all this area here. And so we want to rotate it about the line x equals 1. Okay. So we're going to assume that that is x equals 1 is right here, and draw this line here. Okay. Now, the one thing that we don't know right now is where all three of these particular curves intersect each other. Okay. So if we look, we know that if we take square root of x and y equals 1, and we set those equal to each other, we can find out where they intersect. And of course, by squaring both sides here, I would just get x is equal to 1. So right where you see here, this is going to be the intersection point, and it just so happens to be the same place, well, a point where this x coordinate is the same as the line that goes through it. Okay. So now that we have that, we know that this is the axis of rotation. And how we decide with solids of revolution, how we're going to actually figure out if we're going to use what's called the disk method or the washer method, is we ask ourselves, is there a gap in between the area and the axis of rotation? And so if we look here, we clearly see that it is. So this means we're going to have to define what our outer radius is as well as what our inner radius is. And we need to know that because, of course, our formula for the area here is going to be, area is just going to be pi times outer radius squared minus inner radius squared. So we need to find out what that's going to be. The other thing that we need to figure out is, are we integrating with respect to x or integrating with respect to y? Since our axis of rotation is x equals 1, it's a vertical line, that means we are going to integrate with respect to y. So what that tells me also is that when we look at our closed interval to find the area, which we're calling C and D, C is going to be 0 and D is going to be 1. So we basically know what our limits of integration are. Okay, so now let's try to define what our outer radius and our inner radius are. And so the first thing that we need to look at is, how are we actually going to define the outer radius? So if we look here, the outer radius will be this length right here. So it'll be from x equals 1 all the way to the y-axis, x equals 0. Okay. The inner radius will be from x equals 1 to our parabola here. Well, I shouldn't say parabola, square root function. Now, notice that we said that we are integrating with respect to y. So we're going to have dy in our integration. But notice that our functions are defined in terms of x. So we need to take this and rewrite it in terms of x. So to do that, of course, what we could do is square both sides of this equation. And when we do that, we just get y squared is equal to x. And that didn't turn out so good. So let me try again. That would just be y squared is equal to x. So when we look at the outer radius, we can tell that the length from x equals 1 to x equals 0 here is just a length of 1. Okay, so that's one way we could look at it. We can also look at our inner radius and define this as just the distance of 1 going from here to here. But what we're taking out is this length from here to here, which is what y squared is. So literally we could say this is just 1 take away y squared. Okay. Now that's one way that we could look at it. Now another way that we could do this, and we'll still end up with the same answer either way, is that we could define everything as the difference in between what curve you're at minus the axis of rotation. Okay, and so I'm just going to write this here as an alternative. So if we did it that way, then of course we stop here at x equals 0. And then of course that's the difference in between x equals 0 and x equals 1, which would give us a result of -1. And again, I realize that the radius actually represents a distance. And in this case, it seems kind of odd to have distance be negative. But what we're actually doing is doing the difference of two functions. So what this really is saying here is that the difference in between x equals 0 and x equals 1 in terms of x equals 1 is 1 unit to the left, 1 unit negative. So if you can think of it that way, okay? So in terms of x equals 1, to get to x equals 0, you got to go over 1 unit to the left, okay? So if we think about it that way and do the same thing for the inner radius, then of course what we can do here is we can say, all right, well, this is the difference in between where we stop here, which is y squared. Let's try that again. Difference in between y squared and the line x equals 1, okay? So you can see that what I have here for the outer radius and inner radius is the exact opposite or the negative of what I have here. And of course, the reason why we still end up getting the same answer either way we define it is because, of course, here we have to square the outer radius and the inner radius. So it ends up just being the same regardless of how we do it here, okay? So I'm going to take this approach here and just use it because I think most people, if you're working this out, you probably understand, hey, the distance in between this curve and this curve is 1 unit, and the distance in between here and here is just all of 1 take away what y squared is. So I think that's a little better. Personally, I do this because sometimes when the functions get a little difficult, I just kind of like to see where I begin, where I end, and just define those functions or curves that way and just do the difference of it. But either way, you get the same thing. So I'm going to go ahead and erase this portion here, and we'll continue on with the problem from that point. So now that we know what our outer and inner radius is, of course, r sub 0 squared is just going to be 1. And our inner radius squared is going to be 1 minus y squared, which will just be 1 minus 2y squared plus y raised to the 4. Okay? And then from that, our area in terms of y here, so let's get that here. Our area in terms of y will now just be pi times outer radius squared minus inner radius squared. And that will just be 1 minus all of this. And this will come out to be a 1 minus 1. Of course, we'll now distribute negative all three terms there. 1 minus 1 plus y to the fourth, plus 2y squared minus y to the fourth. And then, of course, the 1 minus 1 here, that part cancels to 0. So this part here just cancels to 0. And all we have left is the pi times 2y squared minus y to the fourth. Okay. And so just to prove my point here, I'm going to scroll down a bit. And let's say if we were to use the r sub 0 to be negative 1 and the r sub I being y squared minus 1, we would still end up with the same thing because ro squared would be 1 still, because negative 1 squared is 1, and r sub I squared would have just been y to the fourth minus 2 times y squared plus 1. And of course, doing the difference in between r sub 0 squared and r sub I squared would have been 1 and then minus all this business here. And then, of course, when we distribute, you'll see that we have the 1 minus y to the fourth plus 2y squared minus 1. And this 1 and that minus 1 go to 0. And you still see that we have a positive 2y squared and a minus y to the fourth. So that's why I was saying, regardless of whether we use this or this, we would get the same thing. Okay. So I'm going to go ahead and erase this bottom part here, and then after that, we'll go ahead and finish the problem. So now that we have our area written in terms of y, we know that our volume now is just going to be the volume from 0 to 1 of a sub y dy, where the area is just pi times 2y squared minus y to the fourth dy. And of course, from here, we'll just do antiderivative of both terms and finish it out. So we got just stick pi on the outside. The antiderivative of y squared is just y cubed divided by 3. So that ends up giving us 2/3 y cubed minus antiderivative of y to the fourth is y to the fifth divided by 5. And all that will be evaluated from 0 to 1. So we'll come here and finish it out. So we got pi, and then of course when we plug in 1, we'll have 2/3 times 1 cubed minus 1/5, 1 raised to the 5. And then for the second one, we plug in 0, it'll be 0 for both terms there. So we just put 0. And then we just end up having 2/3 minus 1/5. And of course, if we do 5 times 2 is 10, minus 3 times 1 is 3, all that divided by 5 times 3, which is 15. Then we just have a case here where we end up with 7 pi over 15 cubic units. So that is how we calculate the volume of the solid that's made by taking the area that we had defined above here and rotate it about this particular axis or line x equals 1. All right, so we'll go ahead and move to the next example. So for this next example, we want to find the volume of the solid generated by revolving the region that's bounded by the parabola 2x squared plus 1 and the line 2x plus 14, and we want to rotate it about the x-axis, okay? And notice that the x-axis, of course, is a horizontal line. So that means, for starters, before we even begin, we know that we're going to be integrating with respect to x. So our formula for volume here is going to be this. And what we're trying to do is figure out how are we going to characterize the area a sub x. So I'll make that a look a little better here. All right, so first thing we need to do is kind of figure out what's going on. So we're going to sketch a graph of these two curves and see what area is actually bounded in between the two. So let's look here, let's draw a graph, and we know that 2x squared plus 1, that's a parabola. So we'll come here, and so that will look something like this. And the line 2x plus 14 is a line with a positive slope. And let's say if that's, well, actually, I have this parabola a little bit too high here. So what I'm going to do is erase this and draw this down a bit, kind of get this a little bit more realistic. So let's say 1 would be right there, and this parabola would be like this. And it would come like this on the other side. And let's say y-intercept for 14 would be there. And let's say the other curve here would be going like this. And I'll go ahead and switch colors so that we can see the difference in between the two curves. All right, so here, we'll have a line kind of coming through like this. And this would be our line y equals 2x plus 14. And of course, our parabola is going to be the 2x squared plus 1. So we'll go ahead and write that in. So y equals 2x squared plus 1. All right, so now, hope you notice that we want the area that's bounded by these two curves. So we want all the area that is inside here. And of course, we see it intersects here and here. So we need to find out those points of intersection as well. All right, so here we have point of intersection here, and we have point of intersection there. And we need to find out what this particular x value would be here. Call this x1, this x2, or we can just simply call it a and b. That's probably a better way to do it, since we're going along with the limits of integration here. And of course, we want all this area that is inside here. All right, so now that we kind of know what's going on here as far as the graph is concerned, we know that we need to rotate about the x-axis. So we'll go ahead and label that here, x-axis. And we know that we're going to rotate about it. So have that, and we know that that means that we're going to integrate with respect to x. So now what we need to do is figure out where do these two functions intersect. So to do that, we just set them equal to each other and solve for x. So if we do that, then of course there'll be 2x squared. We'll subtract 2x from both sides, and here we'll subtract 14 from both sides, and we have 1 minus 14, which will give us negative 13. And of course, from there, if you're looking at this, you probably figured out really quick that we can't factor that. So what we need to do is, of course, in this case, we can either, I guess, do completing the square or the quadratic formula. So I think more people are familiar with the quadratic formula, so we'll just go ahead and do that. So that'll be a minus b, which is negative 2, plus or minus b squared, again, which is negative 2 squared, minus 4a, which is 2c, which is negative 13. And all of that will be divided by 2a, and a is 2. All right, so from here, we know that this is just going to be 2 plus or minus square root, and we'll have negative 2 squared is 4. And we have a negative times a negative, so that's plus. And then we have, here we have 4 times 2 is 8. And then 8 times 13, they give you 104. So we'll come here and put 104. Got stuck there. And all that divided by 4. And then from here, that's 2 plus or minus, of course, this is square root of 108. All that divided by 4. One of the things that we know here is that, of course, 108 is the same thing as 12 times 9, which, of course, we know 12 is also 4 times 3. So we could look at this as 36 times 3, and that would be an easy way to break this down. So this would be 2 plus or minus square root of 36 times square root of 3 all over 4. And we know that square root of 36 is 6. So what we end up having here is 2 plus or minus 6 root 3 all over 4. And then finally, if we break this up into two fractions, we'll have 2 over 4 plus or minus 6 root 3 over 4, which simplifies to 1/2 plus or minus 3 root 3 all over 2. And so these are our two values here, and the x1 and the x2, and this just so happens to be what our a and our b would be as well. Okay, so we do have our 2 points of intersection here. Of course, the 1/2 minus root 3 times root 3 over 2, that should be our value for a, and our 1/2 plus 3 root 3 over 2 should be our b. So now that we have our limits of integration here, we can pretty much figure out what the outer radius and the inner radius are, and then after that, put everything together and finish up. So I'll go ahead and erase what I have here. I will go back up and sort of model the outer and the inner radius, and then put everything together. All right, so we know what our values for A and B are here, but we still do not know how we're going to model this area. One of the things that we do know is that we're going to use the washer method here. And we know that we're going to use the washer method because there's a gap in between the area and the axis of rotation. So that means we need to find both an inner and outer radius here, okay? So the outer radius will be, and we'll just use this, the outer radius will be here. Let's make that look a little better. And the inner radius will be here. And so the outer radius is just going to be the higher function, which is 2x squared plus 14. The inner radius will just be the lower function, which is the parabola 2x squared plus 1. Okay. And so now, of course, what we need to do is find out what r sub 0 squared is and what r sub I squared is so that we can subtract the two. So, of course, in doing this, squared, if we FOIL this out, that'll actually end up being 4x squared. And then we'll have 14 times 2 is 26. So two of those, that will be 52x. And then, of course, 14 squared, which I believe is 196, if I'm correct. All right. Oh, yeah. So here, yeah, I made a mistake. So 2 times 14 is 28, and 28 times 2 is 56. So let me change that right quick. So let's go here. That's 56. And so for the inner radius squared, same kind of thing. If we multiply this out, this will be 4x raised to the 4. And then we got 1 times 2x squared times 2 of those, which is plus 4x squared. And then we square the last term there. So 1 squared is just 1. So we're good on that. And then, of course, we just do the difference in between these two. And so if we did that, that would be 4x squared plus 56x plus 96 and minus, I'm going to make all these terms negative here, minus 4x to the 4th minus 4x squared minus 1. And so that will end up looking like 4x squared minus 4x squared, so that will cancel to 0, so we need to get rid of that. And we will have 56x 196 minus 1 is plus 195, and then we'll have the minus 4x to the 4th remaining. And so that is how we would characterize the difference in between the squares of the inner and outer radius. And so now, of course, the area in terms of x would just be pi times all of this, the difference in between the square of the inner and outer radius. And of course, that would be real simple. Just multiply everything by pi. So I'm not going to waste time doing that here. So I'll just go ahead and go down and start to do the integration to finish the problem. All right, so section some of this stuff off here. So this part was just finding out what our A and B was. This part here is actually trying to get to the area. So our volume is just going to be A to B, A sub x dx, which will be pi. We'll put that on the outside from A to B, and our difference in between the inner and outer radius is just 56x plus 195 minus 4x to the fourth, all that times dx. And so now from here, we will just take antiderivatives and do net change theorem. So antiderivative of 56x is just 56x squared divided by 2. Antiderivative of 195 is just 195x. Antiderivative of 4x to the fourth is 4x to the fifth divided by 5. And all of that will be evaluated from A to B. And so I'm strategically keeping it as A to B until we get to the very end, because we only want to plug in this horrid looking number only one time. So from there, of course, 56 divided by 2 is 28. This will be 28x squared plus 195x minus 4/5 x to the fifth, and all that will be from A to B. And then we'll go ahead and substitute everything in now. So we'll have 28. Just do it like this. So 28 times 1/2 plus 3√3 over 2 squared plus 195 times 1/2 3√3 over 2 minus 4/5 1/2 plus 3√3 over 2, all that raised to the fifth. And that's that, minus, and now we'll do the same thing, but we'll plug in the negative here. So it's 28, 1/2 minus all this business, and I'll just write it and spare you the boring details. Over 2 raised to the fifth, and that was supposed to be minus there, so let me correct that. And of course, that's all of what you see here minus all of what you see here. And of course, if we go and just put that into our calculators and calculate, what you'll see is you'll get something like this, 2,820.820771 cubic units. And of course, if we're rounding to, let's say 2 decimal places, then we'll just round to 0.82 cubic units. And that would be our final answer for that example. All right, so this concludes the first 2 examples of trying to calculate the volume of a solid, where we're actually taking an area and rotating it about a vertical or horizontal line. And so we call these forming volumes by solids of revolution. If you're interested in more examples, I do have a part 2 to this video. And so if you need to see more examples, check that out.